Hello students, in this video we are going to continue lecture series on topic power system stability under the subject power system analysis. In this video we are going to discuss the points in which the first point is factors affecting the transient stability. The second one is the equal area criteria for a transient stability study. So before going to start the actual point, just we'll revise the point which is covered till now. We are having the idea that in case of the power system stability, the syllabus point are nothing but concept of steady state, dynamic and transient stability of the power system and the factors controlling each. Steady state stability, its evaluation and variation of limit of stability under system condition. Then concept of the transient stability, the swing equation and its derivation. So up to this point we had covered in the lecture series, lecture number 1 and 2 on power system stability. Now in today's lecture we have to cover the factors affecting the transient stability and equal area criteria. So till now in lecture series number 1 and 2 we have discussed that the term stability is closely related with the synchronism. Then we had discussed that the IEEE what are the different type of the stability, like rotor angle stability, frequency stability and voltage stability. Then the definition of the IEEE definition of the stability, that is stability can be defined as it is the ability of an electrical power system for given initial operating condition to regain a state of operating equilibrium after being subjected to a physical disturbance with most system variables bounded so that practically the entire system remain intact. Then we had seen the classification of the stability, that is steady state, dynamic and transient stability. Then in case of the steady state stability, we had discussed that the steady state stability limit of particular power system is defined as maximum power that can be transmitted to the receiving end without loss of synchronism. And normally the steady state stability limit does not take severe turn to collapse the system and has comparatively larger limit. Then there is fixed criteria in case of the steady state stability, that is whenever del is less than 90 degrees system is stable, when del is equal to 90 degrees system is critically stable, and when del is greater than 90 degrees system is unstable. Then the power which is transmitted to the through the transmission line to the receiving end is given by the equation P is equal to magnitude of E into magnitude of P upon X into sin del. Then we have discussed different factors which affect the steady state stability and methods of the improving steady state stability. Then in case of the dynamic stability, we have discussed that this stability came into the system when load is frequently changed and has no specific amplitude. Dynamic stability can be significantly improved through the use of the power system stabilizer, and it has comparatively lower value than the steady state stability limit. Then we had started with the discussion about the transient stability. As the word transient, that means the type of the disturbances or the disturbances which are available in this case are for less duration but which are having the severe impact. We are having the idea that in this case mostly we consider the phenomena usually occurring within 1 second for generator close to the cause of disturbance. Then in case of the transient stability, very sensitive protection system is needed to overcome the effect of transient stability. Then we have discussed about the dynamics of the synchronous motion, that is derivation, and some conclusion points related to the dynamics of the synchronous motion. Then we have discussed about the swing equation and the corresponding derivation to obtain the swing equation. So we have discussed that swing equation is given by h upon pi f d square del by dt square is equal to pm minus pe per unit. And in conclusion point, we have discussed that this swing equation is non-linear second order differential equation. Then we had seen the concept of multi-machine system, that is when number of machines are connected together similar to the complex system which is present to provide the electricity to the consumer. Then how the machines swing coherently in case of the multi-machine system. Then we had solved numerical to obtain some basic parameters And in case of the transient stability, we concluded that there is no generalized criteria available for determining the system stability with large disturbances called as the transient stability. And then we had discussed different assumptions which are considered for the transient stability. And in conclusion, we had discussed that the equal area criteria method is to determine the transient stability. Now we have to start with the point factors affecting or methods of improving the stability. Now before that, first of all, we'll discuss which factors affect the transient stability. The first factor which affects the transient stability is nothing but type and location of the fault. Because in case of the transient stability, mostly we consider the different type of the fault, like sudden change in the mechanical input, then short circuit on one of the parallel line, then short circuit at the middle of the line, etc. And the location, whether that fault is occurred at one end of the line, it is occurred at the middle of the line, or it occurs at the receiving end of the line, that location also matters while deciding the transient stability. And second point, inertia constant. So what is the effect of the inertia constant m of the synchronous machine? Increasing m reduces the angle through which it swings in given time interval. That means whenever the sudden disturbance occur, rotor angle del causes the swing, but if the inertia constant is m is more, at that time this rotor angle swing is less, and offering the method of improving the stability. But it is observed that the increase in the inertia constant m of the machine reduces the angle through which it swings in a given time interval, offering thereby method of improving the stability. But this can be employed in practice because of this cannot be employed in the practice because of the economic reason, and for the reason of slowing down the response of the speed governor loop apart from an excessive rotor weight. That means this method are having the limitation that it will reduces the response of the speed governor loop, and as well as it causes the excessive rotor weight. Then another methods of improving transient stability. Methods of improving transient stability are, first one is the increase of system voltage or use of AVR. So what is the meaning of term AVR here? AVR is nothing but automatic voltage regulator. So whenever the fault takes place on a system, the voltage at all the buses are reduced. At a generator terminal, these are sensed by automatic voltage regulator, which help restore the generator terminal voltage by act within the excitation system. Modern exciter systems having solid state control quickly respond to the bus voltage reduction and can achieve from one and one half cycle gain in critical clearing time for three-phase fault on the HT bus of the generator transformer. That means whenever because of the disturbance due to the there is a reduction in the voltage, it will be automatically sensed by the automatic voltage regulator, and it causes corrective action to maintain the voltage stable. So this is one method of improving the transient stability. Second method, use of high-speed excitation system. As we are having the idea that uh, in case of the transmission line or in case of the power system, we had seen that QV dependency, that is reactive power voltage dependency. So whenever there is decrease in the voltage, at that time excitation should be more. In case of the synchronous generator, to increase the voltage. Whereas whenever the voltage is more, at that time we have to reduce the excitation. So that excitation system should be fast to respond to the disturbances. That means the use of high speed excitation system also improve the transient stability. Then third method is reduction in the system transfer reactance. As we are having the equation P is equal to magnitude of E into magnitude of P upon X into sin del for the power transfer. And from this equation, it is clear that reduction in the reactance, that means improve the power transfer capability. So reduction in the system transfer reactance is one of the method for improving the transient stability. But how this transfer reactance is reduced? For that, there are different methods. The reactance of the transmission line can be decreased by reducing the conductor spacing, or it can be also reduced by increasing the conductor diameter. And one of the most popular method is increasing the number of parallel lines between transmission point is quite often used to reduce the transfer reactance. So these are the different methods for reduction in the system transfer reactance. And last method for improving the transient stability is nothing but use of high speed reclosing breaker. Increasing as the majority of the faults are transient nature, in case of the transient stability, rapid switching and isolation of unhealthy lines followed by reclosing has been shown earlier to be a great help in improving the system stability margin. The modern circuit breaker technology has now made it possible for line clearing to be done as fast as in 2 cycles. So, immediately after occurrence of the fault, if the unhealthy system is removed from the healthy one, then it will help to improve the transient stability. So these are the different methods for method of improving the transient stability. Now next point is equal area criteria. In exam there is repeatedly asked question, write the statement of the equal area criteria or prove the equal area criteria method for one machine connected to the infinite bus system. So before going to start the actual equal area criteria method, just we do the some discussion regarding the transient stability. Whenever we had discussed the different type of the stability like steady state stability, transient stability, dynamic stability, at that time we had discussed that in case of the steady state stability, there is fixed criteria for determine the stability. Like whenever del is less than 90-degree, system is stable. When del is equal to 90-degree, system is critically stable. And when del is greater than 90-degree, system is unstable. But such fixed criteria is not available while determining the transient stability. In case of the transient stability, mostly we list out the different type of the fault which are severe. For example, three-phase short circuit fault, then sudden change in the mechanical input, etc. And we try to obtain the stability for each of the uh, disturbance which are considered under the transient stability. So what is meant by the equal area criteria method? Actually, there are two different methods for determining the transient stability. First one, equal area criteria method, and second one is the point by point method. In case of the equal area criteria method, you will get the idea about the critical clearing angle. So what is meant by the critical clearing angle? It is the maximum angle through which the system will remain stable. But whenever del is greater than this critical clearing angle, your system becomes unstable. So that critical clearing angle is calculated by using the equal area criteria. But the limitation of the equal area criteria is that we cannot calculate the critical clearing time. So what is meant by the critical clearing time? It is the maximum permissible time beyond which if the system fault is persist or it remains continue, then your system becomes unstable. So that maximum that critical clearing time cannot be calculated by using the equal area criteria method. This is the limitation of equal area criteria method. So for calculation of that critical clearing time, the point by point method is used. But if you go through your syllabus, you have to study the equal area criteria, and it is limited up to the sudden change in the mechanical input fault only. That's why we'll study equal area criteria method. We'll list out the different faults and we'll study the equal area criteria for first fault only, that is sudden change in the mechanical input. So in exam there is repeatedly asked question, derive the equal area criteria. So we'll start, before going to start the equal area criteria, just go through the figure 12.19. It is variation of rotor angle del with respect to time. That means it is the swing curve, but it is given for both condition. When the system is stable during the normal condition, as well as whenever the fault is occurred, your system becomes unstable. So from the graph, it is clear that when del continuously goes on increasing, that is the graph shows it is shown by the straight line, then your system is unstable. Whereas if del goes on increasing and it becomes stationary at some maximum point where d del by dt is equal to 0 and then start to reduce, then we can say that the system is stable. That means when the system is stable, your del is having variation, but it is having non-linear variation. It goes up to the maximum value, then start to reduce, and then again goes to increase. And this is the graph which shows the system is in stable condition. Now, in a system where one machine is swinging with respect to infinite bus, so for the infinite bus, we had already seen what is meant by the infinite bus. Infinite bus is nothing but in which voltage and frequencies remains stable, although there is change in the load, and that bus is called as the infinite bus. So, for the equilibrium criteria, we consider the one machine swinging with respect to an infinite bus. Then it is possible to study the transient stability by means of the simple criteria without restoring the numerical solution of swing equation. Now, consider the swing equation we had discussed during the last lecture. Swing equation is given by d square del by dt square is equal to 1 upon m pm minus pe. There pm is nothing but mechanical power input and p is nothing but electrical power output. But pm minus p difference is given by pa, and hence swing equation becomes d square del by dt square is equal to pa upon m, where pa is called as the accelerating power and m is called as the inertia constant, which is given by the h upon pi m in per unit system. Now, if the system from the graph, it is clear that system is stable if d del by dt is equal to 0, and it is unstable if del continuously goes on increasing. So we can this fact can be stated as stability criteria, that the system is stable if d del by dt is equal to 0, which is given by equation 12.54, and it is unstable if del by dt is greater than 0. Now, for a sufficiently long time, the stability criteria for power system stated above can be converted into the simple and easily applicable form for a single machine infinite bus system. So, multiplying the swing equation both sides by 2d del by dt, then your equation will become 2d del by dt into d square del by dt square is equal to 2 p upon m d del by dt. So, integrating we will get d del by dt is equal to 2 upon m integration del 0 to del pa d del raised to 1 half. And here del 0 is nothing but initial rotor angle before it begins to swing due to the disturbance. So from this equation, the condition for the stability can be written as 2 upon m integration del 0 to del pa d del raised to 1 half is equal to 0, or it can be given as integration del 0 to del pa d del is equal to 0. So this is the final equation, and from which we can write the condition of stability can therefore be stated as the system is stable if the area under Pa accelerating power dash del curve reduces to 0 at some value of del. But this area of acceleration area under the Pa del curve is nothing but it consists of two parts, accelerating area and decelerating area. Hence, in other words, we can say that the positive or accelerating area under the Pa del curve must equal to the negative or decelerating area, and hence the name equal area criteria. That means why this criteria is called as the equal area criteria, because here we are considering the two area, that is accelerating area and decelerating area, and this both areas should be equal, then only your system is remain stable, and that's why this criteria is called as the equal area criteria. Now, what is the method in this case? As we had already discussed, in case of the equal area criteria method, mostly we list out the different type of the fault which occur in case of the transient stability, and then we apply the equal area criteria for each of the disturbance. So, what are the different type of the fault which are considered under the transient stability? These are nothing but, first one is the sudden change in the mechanical input, second one effect of clearing time on stability, Third one, sudden loss of one of parallel lines. Fourth one, sudden short circuit on one of parallel. But in this case, we consider the different location of short circuit fault, like short circuit at one end of the line, short circuit away from the line end, and effect of the automatic reclosures. But now, in exam, if there is question, you have to derive the equal area criteria. You have to list out this type, different type of the disturbances, but you have to study the first type of the disturbance in detail, because remaining type of the disturbances and the point by point method, that point will be covered in the next semester syllabus under the subject operation and control of the power system. So now we'll study the sudden equal area criteria for sudden change in the mechanical input. Now here we will consider the one machine connected to the infinite bus system. That is, suppose there is the generator, Pm is the mechanical power input, then generator is given by magnitude of E dash at an angle of del. There del is nothing but rotor angle. Then transfer reactance, it is divided into the XD dash, that is subtransient direct axis reactance, and XC, that is equivalent reactance of the transmission line, and it is connected to the infinite bus. So at the infinite bus voltage is magnitude of P. Now we are having the generalized equation for power transfer from generator to the infinite bus is P is equal to magnitude of E dash magnitude of E into magnitude of P upon X into sin del, where X is the transfer reactance. But in this case, transfer reactance is consist of two components, XD dash and XE. Therefore, the system will, this equation will be modified as P is equal to magnitude of E dash into magnitude of P upon XD dash plus XE into sin del. That is, it is given by P max into sin del. Now we'll go through the diagram for sudden change in the mechanical input. So it is the graph between the electrical power power versus del. So P is the electrical power. Then initially that in power is PM0, which is at an angle of rotor angle del 0. But whenever there is power is suddenly increased from PM0 to PM1, then it becomes PM1, and rotor angle changes from del 0 to del 1. Then A1 is the area of acceleration and A2 is the area of deceleration. So first of all, what is meant by the area of acceleration and area of deceleration? So it is clear that whenever Pm, that is mechanical power, is greater than electrical power P, at that time machine will start to accelerate and speed goes on increasing, and that area is called as the area of acceleration. Whereas whenever the mechanical power is less than electrical power output, machine will decelerate, its speed goes on decreasing, and that area is called as the area of deceleration. And generalized equation for electrical power, P is equal to P max into sin del. Now under steady state operating condition, that is at point A, PM0, that is initial mechanical power, is equal to electrical power output P0 is equal to P max into sin del 0. This is the normal condition whenever any generator is supplied power to the load, that is mechanical power input, and it is equal to the electrical power output. Now this point is indicated by the point A in P del curve. Now let the mechanical input to the rotor be suddenly increased from PM1 by opening the steam valve. That is, suppose this is the stable point A. The accelerating power Pa is equal to PM1 minus P causes the rotor speed to increase. That is, whenever this PM0 is increased from PM0 to PM1, this area of acceleration, that is accelerating power, goes on increasing, and speed is also goes on increasing in this case, and hence actually there is a speed to increase from omega, that is increasing speed. Omega is greater than omega s, and does the rotor angle. So the rotor angle at point angle del 1, it will be shifted from del 0. So at an angle del 1, Pa is equal to accelerating power is equal to Pm1 minus P, and it is given by P max into sin del 1, that is new rotor angle, and it is equal to 0 as per the stability condition. But the rotor angle del, it is observed that rotor angle del continues to increase as omega is greater than omega s, that is speed goes on increasing, and hence this del 1 again continuously goes on increasing and becomes negative. That is, that area is called as the decelerating area, and the rotor speed begins to reduce but the angle continues to increase. That is, rotor speed start to decrease but angle continues to increase, and hence it causes the another area A2, which is called as the area of deceleration. So at an angle of del 2, W is equal to Ws once again at steady point C, and the decelerating area A2 equals the accelerating area A1, such as integration of del 0 to del 1 PAT del is equal to 0. Since the rotor is decelerating, the speed reduces below Ws and the rotor angle begins to reduce. The state point now transfers the P del curve in opposite direction. It is immediately seen that the system will accelerate about the new steady state point B del is equal to del 1 with angle exertion up to the del 0 and del 2. That means this angle, rotor angle, uh, get oscillates between del 0 and del 2, and after some time it sets at point del 1 or settles at point del 1. So these oscillations are similar to the simple harmonic motion of an inertia spring system, except these are not sinusoidal. As the oscillations decay out because of the inherent system damping, the system settles now steady state where Pm1 is equal to P is equal to Pmax sin del 1, and areas A1 and A2 are given by A. That is, area of acceleration A1 is equal to integration del 0 to del 1 Pm1 minus P del, that is this area of acceleration, and area of acceleration A2, that is angle between angle del 1 and del 2, is given by A2 is equal to integration del 1 to del 2 P minus Pm1 d del. So for system to be stable, it should be possible to find the angle del 2 such that A1 is equal to A2. So as Pm1 increase, the limiting condition is finally reached where A1 equals the area above the Pm1 line. So see here, it is the stability point at which the area of acceleration is equal to area of deceleration. Then this point Pm1 is greater than the Pm0. Under this condition, del 2 acquires the maximum value such that del 2 is equal to del max is equal to pi minus del 1. That is pi minus sine inverse of Pm1 upon Pmax. Any further increase in the Pm1 means that the area available for the A2 is less than A1. That is, whenever Pm further increase, the A2 start to decrease, then A1 so exceeds the kinetic energy, causes del to increase the beyond the point C, and the decelerating power changes over the accelerating power within the system, consequently become unstable. It has thus been shown by use of the equal area criteria that there are upper limit to sudden increase in the mechanical input for the system is questioned to remain stable. That is, the system will remain stable even though the rotor may oscillate beyond del is equal to 90 degree, so long as the equal area criteria is met. The condition of del is equal to 90 degree is meant for using steady state stability only and does not apply to the transient stability. So in short, we can say that similar to the steady state stability, there is no fixed criteria, but although del is greater than 90 degree, then also your system is remain stable in case of the equal area criteria method, but only condition is that area of acceleration should be equal to the area of deceleration. So what are the conclusion point regarding the equal area criteria? There is upper limit to sudden increase in the mechanical power for Pm minus P for the system is questioned to remain stable. System will remain stable even though the rotor may oscillate beyond the 90 degree. Only condition is that area of acceleration should be area of deceleration. Then condition of del is equal to 90 degree is meant for using steady state stability only and does not apply to the transient stability case. So thus equal area criteria help to determine the critical clearing angle and not critical clearing time. For critical clearing time, it can be obtained by numerical solution of the swing equation such as point by point method, but it is not part of your syllabus. So with this, there is end of the sixth unit. Thank you.